any theory type question?
You don't have to write a program, but you don't have to write a story either. So I don't know what you mean by theory type questions. My interpretation of theory type questions are where you keep on writing stories, but it's not a story writing question paper as such.
So,
yes.
So can you repeat whatever you said? We just joined. We were in the other meeting. Some of us.
Just hold on. Just hold on. So this was about the examination on next week, which is the exam week. So you will have a continuous assessment. For continuous assessment, you will have a worksheet which will be given to you, and that is something you will have to solve on Wednesday during the class. And then you will get down another thing, which is an exam, which is going to be MCQ based, and that will happen on Friday. Okay. So, and all of these two things are there during the class duration. You have to finish off and submit it during the class duration itself. There is nothing of a take home or take away. The worksheet will not have anything to do with programming, but it does have to do with neural network. So you will be given a neural network and asked some specific questions about the neural network at certain points. So you have to answer them. And the other test, which is on Friday, it's the actual midterm test, and that test is going to be of 2-hour duration during the whole class time. So exactly 1 week from now, and this whole duration 11 to 1 is when you will have it. The number of questions, actually, like the number of questions and the time you spend on each question is going to be commensurate with that. So that's how it's designed, and that's all.
Sir, can you repeat the first statement, like when the assignment will be given? Because I joined a little late.
It will be given on Wednesday. You will get down all of these instructions written. Don't worry. They will be posted on the MS Teams. And in fact, like for the test, there will be 2 different MS Teams which will be created for this purpose. So okay. you will be divided into 2 different test rooms, and like students of which test room, they will be provided with the links. Like these are people in this test room, these are the people in the other test room. That whole thing will be provided to you. Don't worry. By this weekend, you will get down all the instructions about the test.
Sir, questions are MCQ mode in Friday exam.
Yes.
How many questions are there?
And that's what I said. It will be enough to keep you occupied for 2 hours, but I cannot tell you how many.
Is there a class on Thursday? Because next week many exam. So
next week you only have these exams. These 2 days. That's what I gave you a heads up. Other than that, I'm not taking class on the Thursday.
Okay, sir. Thank you.
किंतु Okay, so today I'm going to start with this thing which is called as receiver operating characteristics, and essentially this builds on what we had done yesterday. So we did write down something about a confusion matrix. And if the ground truth is positive and the prediction is negative, then what is that called?
False negative.
Could you repeat?
If the ground truth is positive and the prediction is negative, then what is it called?
False negatives.
Negative.
And if the ground truth is negative and the prediction is positive?
False positive.
Okay. So now, based on this, we did define some metrics like accuracy and others, but I'm specifically looking down at these two metrics, which is sensitivity. So what was sensitivity defined as?
True positive upon true positive plus false negative.
So it's essentially true positive divided by all positives. Okay.
Excuse.
Sir,
Yes.
are you writing something?
Oh, you guys are not able to see it, right? Just hold on. Yes, I am writing. This is that weird thing. It does not refresh if it is below some window. Now you're able to see it, right?
Yes, sir.
No, I am sorry for that. This just the Teams window came above it, and then this wasn't getting refreshed. Minimize this Teams window. Just a minute. I'm trying to juggle between the windows so that I can still manage to see the chat. Hey. Okay, and then there was another thing which is called a specificity. So what was specificity defined as?
False negative upon
True negative.
the negatives.
False negative upon false negative plus true negative. Was it so?
True negative.
No, so it
True
should be
negative.
different.
True negative upon true negative plus false positive.
False positive.
True negative upon true negative plus false positive. Okay. So this is essentially true negatives divided by all negatives. Okay. So now using this, what would you get? So say I have a model. So this is some sort of a deep neural network. Input to this is X. Output from this is Y. Okay. Now say this Y is something like Y1, Y2. Okay. So now over here, if these Y's are essentially prediction, put on this hat. Now, if Y1, Y2, they are all range limited. So these belong to the range of 0 to 1. Okay, say that there is some probability over there based on which I'm doing. And this is the neuron for positive class, and this is the neuron for negative class. Now, typically, one of the decisions. So one of the decisions is argmax. So what does argmax essentially do? So argmax will do that this predicted class label is equal to argmax over this y of omega. So what it says that if for whichever the value of this y is highest, so that class is going to come out over here. Now, if we do this kind of a decision, so there will be a fixed value observed for sensitivity and specificity. This is what will be seen. Do you agree or not to this one?
Sir, what is SN and SP?
So SN is sensitivity and SP is specificity. So this is just a short form, SN and SP. Okay. So do you think that there will be a fixed value of sensitivity and specificity which you will observe?
Sir,
Yes.
sir, can you explain this confusion matrix part a bit more? I'm getting confused in that.
Were you there in
Yes,
yesterday's
yes,
class?
sir. Could you
Yes, sir.
repeat the in term of with work, sir? Every T and FN.
Okay. Okay. So say that what do we have? So let us have some. Say there is an image x1, there is another image x2, there is another image x3. Like this, it keeps on going up to x capital N. Okay, there are capital N number of images over there. Now this is my input image. Now I have a class label. So if this image was that of a cat, then I write down a cat. If this image was a dog, then I write down a dog. Then if this one is a zebra, like this I keep on doing, and maybe this one is a cat. Okay. Now I look at what is my, so this is my ground truth, exactly what my object is supposed to be. Now I look my prediction. So now this first image, which was a cat, got predicted as a cat. The second image, which was a dog, also got predicted as a cat. The third image, which was a zebra, got predicted as a dog. Like this, it keeps on going. And the last image, which was a cat, got predicted as a zebra. Okay. So now if I want to look at my confusion matrix, for the class cat, for this particular class. Okay. So now my positive is cat, negative is all other animals other than cat. Okay, cat complementary, that is what my negative class will belong to. So now looking at this whole thing, if I look into my prediction, is going to have positive, negative my ground truth will also have positive and negative. So now let us count. So how many cats got actually predicted as cat? So that is what entry will come over here. So it was actually a cat and it also got predicted as a cat. So there is this scenario that there was one cat which got predicted as a cat. In no other instance, there is a cat which got predicted. So here the cat did not get predicted as a cat. It was wrong. Okay, so I see 1. I write down 1 over here. Okay, so I will make it simpler. I will actually make it x4 so that there are only 4 such conditions which come down and you can see a complete table. Now let's look into the other condition. I have a positive which gets predicted as a negative, which is I have a cat, but it got predicted as some animal which is not a cat. So how many scenarios do I have? I have a cat which got predicted as zebra, which is not a cat. So here my value is 1. Okay. Next, I look at an animal which is not a cat, but got predicted as a cat. So you see this scenario, there was an animal dog which got predicted as a cat. So here it becomes 1. Okay. And then you have an animal which is not a cat, which got predicted as not a cat. So there was a zebra which got predicted as a dog. I mean, a zebra did not get predicted as a zebra, so that way it's wrong. But the point is I'm looking only at this class of cat over here. So with respect to cat, what is happening? So with respect to cat, an animal which is not a cat got predicted as an animal which is not a cat. So this is also going to be 1. So now let's look into this one. So this comes because of this. Next, this comes because of this. This one comes because of this. This one comes because of this. Okay, so this thing over here, what do I call it? So what is this thing called?
False negative.
False negative. Okay. What is this thing called?
False positive.
Now what is this element called?
True negative.
And this is true positive. So now is this clear to you how this confusion matrix comes?
Yes, sir.
Sir, will it be always defined for a class, or can we define it for all the classes as well?
Yeah, you can actually define it for all the classes. That will be a multi-class confusion matrix. The only thing is that in a multi-class confusion matrix, you can only comment on the accuracy. You cannot comment anything on the sensitivity or specificity in any way.
Okay.
So in the last slide, you wrote like one of the decision is argmax, and then you said omega hat equals to argmax of y hat, sir. So what is this omega is, sir?
So omega is. How come you guys forget everything? So omega is a class label. So if there are say let me use a different color. Say there are n number of classes, then capital omega is a set which belongs to these labels, small omega 1, omega 2, like this up to omega n. So this is a label given for cat, dog, zebra, elephant, like that it keeps on going. So that it's just an sort of like it's essentially a label, that's it. Okay, is that clear to you?
Yes, sir.
Okay, so now from an experiment, if you are using this argmax, then you will get a fixed value of sensitivity specificity. Is it so? Do you agree that if I have this argmax kind of a argument being used, then every time I get the same value of sensitivity and specificity? Come on.
Sir, what is meant by every time here? Like, is it after every iteration?
No, this is after training of the. What did we do yesterday? Were you even present in yesterday's class? I'm just continuing from yesterday's class. You did the whole validation. When do you do the validation? When is your validation?
After the training. After the training.
After the whole training process. So after the training process is over and then you run down a validation, then whatever is the sensitivity and specificity, that is going to be a fixed value which you get.
Yes.
Yes, sir.
Okay. Now, instead of that, I come to another kind of a decision. Okay. Which is called as a threshold based decision. Okay. So now in a threshold based decision, what will happen is something like this. So say I have this X which goes into my neural network. And from here, I get this prediction Y. And what I said is this Y is a 2-class prediction, Y1, Y2. Okay. So this I can say is a cat. And this maybe is not a cat. This kind of a scenario. Now what I'm saying is that omega for cat is equal to true if y1 is greater than a certain threshold theta or 0 otherwise. So essentially what I'm doing is now say theta 1. So now we make the decision subjective to the threshold. So that theta 1 is a very important factor which becomes as of now. So what we end up doing is something like this, that I have this DNN, taken my X, I get my Y, and now I put that threshold decision function on top of it. And based on that threshold decision function, what I would see is, so let's look into a scenario. Okay, so I have this X1, X2, X3, X4, X5. I have something of this sort, and then I'm looking at this Y1 0.9, 0.7, 0.6, 0.3.2, something of this sort is what I have. Now what I say is that omega 1 what is this omega 1 when theta 1 is equal to say 0.8. In that case, your decision is going to be, this is going to be equal to 1. This will be 0, 0, 0, 0. Okay. Now you can have omega 1 when theta 1 is equal to 0.4, something of this sort. So now when you have this one, then what comes down? So this is 1, this is 1, this is 1, this is 0, this is 0. So likewise, you can continue. So there can be omega 1 when theta 1 is equal to 0.35. So in that case, you get this as 1, 1, 1. This becomes 0, 0. And then it keeps on going like this. Now over here, you also had this actual value of y1. So say, or not y1, but your actual omega 1. So these are all predictions, hats. So you had your actual omega 1 over here. So this is 1, 1, 1, 0, 0. Okay. Now if you carefully look over here, that when I'm looking over here in this particular example, then because this threshold is very high, so the only one sample which was actually a cat got predicted as a cat, whereas two other samples which were also cats did not get predicted as cats over here. Okay. Now I look into the next one where you have a different threshold. Now in this different threshold, what comes out is that 3 examples which were actually cats got predicted as cats, and the 2 examples which are not cats did not get predicted as cats. So sort of like this threshold is a much better option of making this decision, or gives a better susceptibility to this decision than this one. So this is what I would choose as a threshold. I can also choose this as a threshold because over there also I get the same thing, that 3 of them which were actually cats got predicted as cats. 2 of them which were not cats did not get predicted as cats, as in over here. Okay. So now if you look over here, if I keep on varying these thresholds, then in some way my confusion matrix will also vary. Do you agree to that?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So now that my confusion matrix will vary over there, so for every single threshold, I can get a different sensitivity and a different specificity. So from there, we come and we make a interesting plot, which is called as a receiver operating characteristic. So this is sensitivity, and this is 1 minus specificity. Okay, this plot is what is called as a receiver operating characteristics. And what you would see is, or an ROC plot. What you would see is that this is always bound in this area of 0 to 1. So 1 minus specificity basically, so specificity and sensitivity, they are bound in the range of 0 to 1. So your 1 minus specificity is also bound in the range of 0 to 1. Do you agree to that?
Yes, sir.
Yes.
Okay, so my area, maximum area under the ROC is what is also called as AUC. This is equal to 1. Okay, now if that is the scenario, then what you would see is that by varying by varying these thresholds, you would end up getting a plot for every classifier, which will be something like this. So for a certain threshold, you might be getting these points like this. For another classifier, you would get down something which looks like this. For some other classifier, you might have something which looks like this. So what comes out is that, say this is for for deep neural network 1, this is for DNN 3, this is for DNN 2. So for every single neural network, for every DNNi, there would be a separate plot, and the area AUC of the DNNi indicates its quality. Okay, so now I have this question for you, that if each of them has a different plot such that their areas indicate their quality, then which of these deep neural networks do you think is better?
The red one.
DNN1, because it
Okay.
has the most area in all of these.
So the quality will be the best for that.
Why is it so? Why is it that the one with the highest area will have the best quality?
So because like compared to the other curves, we will have at any like point, any vertical or horizontal lines, if we draw and we check at all those points, we will get higher sensitivity and specificity.
So what would it physically indicate?
That we are more like there are that classifier is more sensitive.
So see, if I do an argmax and find it out, then anyways that problem is solved. But then why am I going to do this kind of a soft thresholding, and based on that I generate these plots, and then from there I comment on the quality of this model?
So sensitivity, the definition is basically true positive divided by total number of predicted positive. So
Total number of positives, not predicted positives.
total number of positives. So basically, if the sensitivity is high, that means our classifier is predicting the true positive highly overall. And if since in the rate curve DNN1, the 1 minus sensitivity one minus specificity is basically the total number of false positive in the numerator part. So that is low. So that means our classifier is identifying in the false positive low with high sensitivity. That means it is working very well.
That is okay. My question is that why do I want to get a ROC curve in order to come and comment on that? That I could have anyways done a argmax, found out my sensitivity specificity, and I could have commented.
But with the threshold value, we can like if the probability is low, still we can maintain. We can say that the certain label is that cat or dog, whatever it is, in the true form. If with using argmax we can only predict one.
So is the use of ROC curve so that we can like set the thresholds as such that we get the best so that we are like, say if we are dealing with a medical problem, then we want our like we want to reduce the number of false false positive or false negative, sorry. So
False
then we can
negative is what would focus more on reducing in case of a medical problem
yes,
rather than
yes sir, yes sir. Yeah, we will try to reduce the false negative. So what we can do is we can like increase the specificity and choose the particular point and on the ROC where we see our like 1 minus specificity to be very less, and then also compare the plots of the different and try to see where the our sensitivity is higher for that particular specificity.
Yes, I mean that's definitely one of the uses of ROC. That's definitely one of the uses of ROC. But then I want others to say in the class, did you understand what Hitesh just indicated right now in his response?
Sir, like we can see like for a given threshold which model is performing better and which is predicting the true positives correctly for a given threshold.
So see, essentially, let me answer the first part of it. It requires a bit of deep thinking for each of it. Now, what this ROC plot is giving me, and or say what this AUC or the area under this curve, this actually gives me is very critical. So first and foremost, it says that I have an objective way of say of suggesting how good a model is irrespective of where I am thresholding. So what it does, it selects multiple thresholds and gets down the area over there, and based on the area, when I am commenting that this is a better model compared to the other one, then what I am essentially doing is that I'm able to say that independent, irrespective of whatever threshold I select, then I'm going to get this model. So what that makes it is that this whole thing becomes much more objective and independent of a threshold at which the performance is being measured. So what I do is I give you a model. You as a product engineer, somebody who is going to incorporate this trained model into your product, you can choose to select whichever threshold you want by essentially, so you can choose to select whichever threshold you want in order to achieve a trade-off between your sensitivity and specificity. So whether you can do, whether you want to maximize on your true positives or you want to minimize on your false negatives is going to be your guidance factor for choosing out a threshold. So this is what you're going to do. And what I give to you is a model which is independent of all of those. So I'm not putting down a fixed threshold or anything on your decision, and I leave it all up to you to do it. So now what I'm doing essentially is that I want to pit multiple such models and say like which of them is the one where you can choose over a wide range of thresholds and still you will have a similar kind of a performance. So if you carefully look, a model which has a higher area, which is closer to that total bound on the area, is the one which will not show a significant variation in its performance, irrespective of the change of threshold which happens over there. Okay, so for a wide range of change in thresholds, you will have a similar kind of a performance, and that's why you will see this saturation in that curve over there. Whereas the one where the performance is going to vary significantly, you would see that the area is going to be lower and lower. Now that makes me come to my next question. What do you think is the lower bound on AUC? Can you tell me what would be the lower bound on AUC? So it will be the lowest value of AUC. Highest value of AUC anyways will be 1. But what will be the lowest value of AUC?
0.
Are you sure?
It won't be 0.
So if you say that it is going to be 0, then the curve is going to look something like this. Only in that scenario you would say that it is 0. Okay. Do you think a curve can be like this? Think about it.
Sir, it should be 0.5, the lowest one.
Why do you think it will be 0.5?
So because that means we are just randomly guessing the value without any kind of model training. That way, the 50% chance that it will be the wrong if binary classifier.
Okay, this is a binary classifier which you are looking. Other than that, you cannot get a discrete value of sensitivity and specificity to work it out. Okay, so if you have a multi-class classification, then for each class you will be considering it to be a binary classifier and then work it out.
Yes, sir.
Now the point is that over here, how can you say that it is going to be, say if you are taking a random guess, then why do you think it will have an area of 0.5? So essentially, it will have an area of 0.5 means that the curve is something like this or like this. And this is not possible as such over here. So the only possibility is this one. So if this is going to be a straight line with a slope of unity, then intercept 0 slope unity straight line as such what it comes out, then why do you think that is the ROC plot which is associated with random guess?
The false negatives and true positives are like uh, is in the same ratio at every point.
Can you take a small example and show it to me?
Sir, because sensitivity has true positives in the in the numerator, and 1 minus specificity has false negatives.
I did not understand. Give me an example. Give me an example.
So like sensitivity has true negative in the numerator and 1 minus sorry, sensitivity has true negative in the numerator, false negative in the numerator, and specificity has true negative in the numerator. So basically they are correlated, like both of them summation will be 1. So if we guess one, let us say we are randomly guessing, then the other one will be automatically the opposite. So the use summation.
What is automatic opposite? So just solve a small example. You asked me, you guys did not understand what was confusion matrix. I did solve this small example to show you. Then in order to show you how this ROC will come, I did this small example for you to understand that how sensitivity and specificity will vary based on threshold. So why don't you give me a small example similarly? Take some values, make a table, and show it. Yeah.
Sir, like when you just explain the confusion matrix to us with an example, like we got the confusion matrix consisting of all the same values, right, sir? Like all the columns were 1. So what
incidentally it came out because I took only 4 conditions and 4 examples.
Okay, so sir, does it have any sort of particular implication, or it is just some sort of a coincidence of the values we took? Like
It's
if all the
it's very coincidental.
Okay.
So it will be hard.
What?
The minimum value half area under the curve.
So my question is, how will it be half? Can you at least show me with an example that it will be half?
Sir, mathematically you can see that
Can you
plus,
write down that and put it on the chat? Let us see. Let all of us try to prove it. Why will it?
Yeah, sir, sensitivity plus specificity equal to 1. So and so if we take sensitivity equal to some Sn and
Wait a minute. Why will sensitivity plus specificity be equal to 1?
Okay, no. sorry, that is okay.
So, sir?
Yes.
On taking the ratio of sensitivity upon 1 minus specificity, and assuming that our distribution is it has total number of negatives and true ground truth is like total number of negatives and total number of positive equal, we get that the ratio of sensitivity and specificity is directly dependent on true positive upon positive minus true positive, which itself is the definition.
Hitesh, we don't speak maths. We write maths.
Okay, sir.
Just write it down, take a picture, share it on the chat.
Hello.
Yep.
So I have posted an image example of in the chat. Can you
Yeah,
confirm
just
if it
open.
is right?
And this is just a sensitivity specificity, but like how does it indicate that a random classifier is going to have the area as 0.5?
So basically, it is an example of x plus like 1 minus specificity plus Sn is equals to 1. So x plus y is equal to 1. That I think.
But where is that curve? I want to see a curve come. You just have one single point. A set of points will give me a curve. And I'm asking you for area under curve. I'm not asking you for a point.
Yes, yes. So I have to similarly I have to create a similar mode examples. Then we have to plot.
Yes, yes, yes. Not more examples. This is where you are forgetting. Your prediction is what you got as 0 and 1, but that is not the case. Look back in when I was showing that example. The prediction is not discrete. The prediction becomes discrete only after the threshold function.
Yes.
So look into this example. Based on the threshold theta, the prediction becomes discrete. But before that, the prediction is not discrete. The prediction is over here, which is more of a continuous.
Yes.
Sir,
Yes.
sir, in a random model, can we assume that true positives, true negatives, false positives, and false negatives are all the same, which is equal to n by 4?
How can you assume that?
Sir, first let's consider the true positives and true negatives. So the model will predict half of them as the correct ones and half as incorrect. Okay. So true positives plus true negatives equals to n by 2, and false positives plus false negatives equals to n by 2. And then we could consider that half of them are of like true positive class and
So,
half.
so do you mean to say that every time it will be so, irrespective of the threshold?
Yes, sir. If we consider that, then the ratio becomes 1
See,
and
this curve, you can get this curve only by varying the threshold. Now, you take a set of predictions, then take a threshold and vary that threshold, and then see what comes out.
Sir, what do we mean by random? Means are we using some distribution based on that we are predicting like Bernoulli P something? Means what do we mean by random guessing? Random exactly.
Random guessing means that okay, so random guess essentially would mean that whatever be the type of x which goes over there, my y is just a random value generated from a uniform distribution. So assume this one that y is generated from uniform distribution in the range of 0 to 1. That's a random guess. You wanted a mathematical definition, I give you this definition. So it's not Gaussian, it's not Poisson, it's not binomial, it's random from a uniform distribution.
Hello, sir.
Yes.
Sir, like, is it completely defined that the minimum value is 0.5? No, I mean, like, there cannot be any other value. Like, I'm getting 0.25.
No.
Okay.
Sir, for a random classifier, sensitivity will be equal to specificity, right, sir?
Why will it be so? You prove it. You show me with the proof that yes, it will be so.
So
yes.
So like I have got that example. Like it is just like by taking a confusion matrix where we have one in true positive and 1000 and like
Can you
two.
just take a photograph and post it on the chat?
Something regarding the proof of getting a straight line of slope 1.
You're saying that probability of true positive is equal to probability of false positive. I did not understand that line.
So because we are saying that we are classifying everything randomly, then anything that can be when we are classifying it positively, then the probability of when something is positive, then when something is being predicted positive, then probability that it can the ground truth value of that thing is positive or negative, it can be equally likely. I am trying to say.
Okay. Let me clarify this one. So what I said is that the prediction which is getting generated is any value in the range of 0 to 1, which is equally likely. That's the only thing which is told to you. I did not say anything about the probability of true positive and probability of false positive. I just told you something about that prediction y, which is getting generated. So y is a random value in the range of 0 to 1, which is drawn from a uniform distribution. That's it. So now, subsequent to that, can you tell me what all other things you will be observing over there?
So when we are getting any number, like whatever prediction we are getting, the probability that it is being predicted correctly and the probability that it is not being predicted correctly, they are equally likely, means I am trying to say that.
How?
Because it can be correct and it cannot be correct. And as we have predicted randomly, so.
No, you are making some guesses. I want you to have a math around it. As simple as that. Prove me.
Sir, sir, if it's a uniform, means equally likely outcome for y, I can, if I'm taking any threshold, suppose it's some p. Okay, so if I'm taking as p, then what I'm doing is basically fraction p of my total data will be predicted as a negative class, and fraction 1 minus p of my data will be predicted as my positive class. So if the this is for the entire data set, irrespective of its actual class, whatever it is. And from the entire set, if I can take a small subset of real.
Hold on. This is something I keep on stressing on all of you guys. Write it down formally, take a picture, send it on the chat. Let me look through it. The reason I'm asking you to do it is when we think in our thought process, we cannot articulate and see everything in front of us. And as a result of which, because I have a motivation that this is my final goal, I want to prove, I will be under an illusion that that is proven. It may not always be so true. So please write it down. Okay. I will leave it to you guys to prove it. And then I will
Sir, I
have
have got it, sir. Sir, just taking pictures, sir. Just give me a minute. Got it.
do it. Okay. I mean, in some way, you are right as well. So this was a solution by Isha. Yeah, I mean, you took a very straightforward case and did it. You did get it. Yeah. And if you extend it out, you will actually get all of those intermediate points as well. So 0.25, 0.25, 0.75, 0.75, and it would go. So you will get down that whole thing. Okay, good. So you guys can actually look into Isha's example. That's the kind of a thing which I was expecting. Okay. Now comes the next part, which is what we called as vector CNNs. Okay. So now
So I have added my solution also, sir.
Hitesh, everything is good except for that I have to tilt my head in order to see it. Okay, yeah, it is right. And guys, please try to be empathetic about the fact that when you post a solution, somebody should not be getting into too much of a pain in order to be able to see your solution. Your thing is like 90-degree rotated.
See, yes, sir.
Remember something. You go to McDonald's in order to buy a burger where they have these glossy looking things presented out over there so that it allures you to buy. So posting your solution also abides by the same rule. It should be something which really motivates someone to look into it. Otherwise, if it doesn't motivate, then it is more of like what traditionally Government of India servants used to do, that they would say like, I did my job. Nobody understands what the outcome of it because there wasn't essentially any outcome. So please don't behave like that kind of a stupid mentality. Okay, so now coming to this next part on vector CNN. So let's take an example. This is something like this, that I have a CNN over here through which I'm predicting some outcome. So initially I give an image of an apple. Okay. And then I give an image in which I have some digit being written. Okay. So when I look into this, so this is my x1, this is my x2. So I'm looking into the prediction over here. So I'll have two predictions. So one is that of my apple class. Another is that of my digit. And over here, this is my prediction of apple. So this is y1 hat, y2 hat, this is y1 hat, and this is that of apple, y2 hat. Now, if I take this and instead of this particular kind of an apple, I actually have a rotated version of this apple being placed over here. Say I rotate, this one becomes x1 dashed, which is rotated x1.
So what is written inside the y2 block, sir? Y2 predicted block, sir? Below apple.
Nothing is actually written inside there.
Okay.
Just a minute. এই ক্লাস নিচ্ছি পরে ফোন করবো। And this is my rotated version, which is x2 dashed. Okay. Now, when I look into my predicted output over here, then what do I get? So for my apple, I would see that this value actually reduces for some reason. In general, I would see that. And this value is as such, it remains like that. Now here also, this value is going to reduce. So this for apple will be like this, but for my digit, this one reduces. So if you carefully look into this one, this is equal to so essentially what it means is that if there is some sort of a perturbation, and that perturbation which I am giving over here is essentially a rotational perturbation. So if there is a perturbation which is given to the input, then my output is also impacted in some way. But let's look at it carefully. So this is a straightforward apple. This is a rotated version of the apple. Now, irrespective of whether it's a rotated version or it's a straight-faced version, it is actually an apple. So the prediction to be coming out for this class of an apple, that should stay as strong as over here. So here also it should be as strong or of that high value as it is over here. But then when I rotated this apple, in general with most CNNs, what you will observe is that this activation value reduces. Similarly, for this digit, if I rotate this digit, in general, we would see that this activation value which was high for the digit, that also reduces over here. So this is a very interesting observation which you will see will come up when you try to rotate these images. Now, based on this, let us understand that what are these different kind of transformations known as. Okay, so say that I have an input x over here. I apply certain kind of a transformation which is g theta and get down over here. This is what is x prime. Okay, now I have a neural network function which is f.
First slide.
Okay, and say that the same function is applied on both the original one and the rotated version. So this is rotation by theta. That is what is known as g theta. So I would get down something which is called as y. Over here, I would get down something which is called as y prime. Now, if between y and y prime, you have this relationship also given by g theta, which essentially means that f of g theta. So what is f of g theta? So f of g theta is essentially this pipeline. Okay, so f of g theta of x, if that is equal to g theta of f of x. So f of x is this part which is y, and I apply g theta on that, so I get y dashed. So either from this root or from this root. So this root is what is defined by this. This root is what is defined by this. If this kind of a relationship holds true, then this is what is called as an equivariant. Relationship. Okay. Now, if I have another thing where, say, I have my x and I do a rotation by theta, I get my x prime, and then I apply an f on this one as well as on this one, and now what I get is a prediction which is y in both the cases. Okay, so what it means essentially, so this transformation is equal to, so if f of g theta of x is equal to f of x, then this thing is what is called as invariant. Okay, now I have another form which is what we call as covariant. So what it does is like this. I have x, I have g theta, on top of it I get x prime, I apply f in either of these cases, and then I get down a prediction y. Okay, now here this is essentially this theta, such that over here I get down y plus theta. So what that means is that and say that this thing is called as g theta prime. So if f of g theta of x is equal to essentially g theta prime of f of x, so this one is essentially this root. So you have g theta of x, which lands this one, which is this inner part, and then f on top of it, which is this outer part, which gives you y plus theta, which is equal to f of x, which is this one. You come over here, you do a g theta prime, so which is y plus theta, and then you end up being over here. So this thing is what is over here. This thing is what is over here. So in this case of this relationship, this is what is called as covariant. Now, today we are going to focus on this particular case, which we call as the invariant transformation.
Sir?
Yes.
So the function g theta rotates the image by theta degrees, right?
Yes.
So then in the predicted value, when we are applying g theta in the y bar, then and it produces y hat bar. So
Okay, which particular case are you saying? Equivariant
sir,
or invariant?
Equivariant.
Okay.
So how is it applying the function? How are we applying the function g theta in the prediction? Because it's not an image, right?
Okay. So over here, if you look carefully, this g theta actually has to be a matrix of some sort on which we can apply that transformation. So it may be an image which is rotated. Actually, this has to be of the same size. Like it has to be 2D in its nature. Otherwise, that rotation, that same kind of a rotation function will not work. So if there is some other kind of a function which gets applied by the same extent, then that becomes covariant. So as in over here, if I was getting some prediction of an angle or something, then I just add this angle on top of it, then it works out. So it's still rotation, but rotation of the angle. So that's a covariant case. Is that clear?
Sir, but how are we applying it to the output? In the, let's say in the equivariant case, we are like considering that first we rotate the image and then we predict. And in the in the other path, we are considering we predict, and then I'm not getting it. How are we rotating the output? Like,
so your output is actually an image as well. So your input is an image, your output is also an image.
oh,
So in the equivariant case, input output both of them are images. Then you can rotate the image.
yes, sir.
Okay. So that's exactly what I'm saying over here. I'm in the middle of a class. I will leave at 1. Okay, so now let me get into the next part of it, which is what is this vector convolution, and that's something which helps us achieve rotational invariant. Yeah, tell me.
Sir, like in case of like equivariant, we were rotating the matrix. Sir, in case of covariant, like you said that g theta prime is basically some theta that is added, right? So plus theta.
So over here, I take this example where I am trying to predict what is the angle in which the object is present. So whether the principal axis of that object is at 0 degree or 30 degree or something of that. So if I rotate the object, if I rotate the image, then the object would have rotated, and accordingly my predicted angle will also have changed.
Sir, but like the output or input, whatever they are in the matrix from, right, sir? They are basically a...
Okay, so now look over here. Y, I did not write y as a tensor. My x is a tensor, but my y is a scalar value.
Okay, so the f is acting on a tensor and the rotation is happening on an image, right, sir?
Yes.
Okay, got it.
So please follow my symbolic conventions. I did introduce that quite long back, saying that if there is a bar below it, then it's a tensor. If nothing is there, then it's a scalar value.
Got it, sir.
Okay. So now the next one is what we call as vector convolution. Okay. So let's look into what a vector convolution looks like. So say I have this image over here, which is X. Okay. And I have a convolution filter. So I can have a convolution filter like this, which is for my case, which is W. Oh, no, let's use the same convention. We are using P. Okay, so this is P1. So if I convolve with P1 plus add a bias B1, then what am I getting? I'm going to get down activation map. Now what I do is I rotate this P1 by theta 1. So I would get down another convolution block over here, which is a rotated version of this one. So this one is what I call as P1 theta 1. So this becomes P1 comma theta 1. Okay. So I can convolve plus add the bias B1, and then I get another channel over here. Now similarly I can rotate by theta 2. So I get P1 theta 2 plus this bias P1, and I get this output, and this keeps on going like this. So this is P1 theta, say theta R. So this is also going to produce an output over here. Now, remember that this is something which I'm doing only for. So this is done only for one of the kernels P1 and not so on the others we will do it. I'm just showing it for one of these kernels what it will look like. Okay, so essentially all of these things can be stacked together and you have another such thing which is getting formed. So this is my set of activations which are all rotated versions of each other such that any one of them can be called as y of r, which is essentially equal to x convolved with p r plus whatever is that bias over there. Okay, so by changing these values of r can value from 1 to 6. In that case, what is going to happen is that everything, so say that r is equal to 6, then so what will you have? You will have p, which is rotated by 60 degrees. You get down the first such rotated version. Then you rotate by 60 plus, wait, if it is 360, 6 is a 36. So this becomes 120 degree. Then you have one more. Now you rotate by 180 degree. Then you get one more. Then you rotate by 240 degree. Then you get one more. Then you rotate by 300 degree. You get one more. So in total, you would see that there are 6 such rotated versions of the kernel which is available. Okay. Now, once this is there, then what we do is that we need to come to a form where we can merge that and get it into a different kind of a representation, which is called as a vector field. So what do we do? So I have these multiple channels of y. So this is my y1 essentially. From here, I apply an operation called as orientation pooling. And this orientation pooling is going to give me something which is called as a vector field. So this vector field is defined as z is equal to rho comma theta. Okay, and this belongs to r power of 2 cross w cross h, am cross n whatsoever, whatever you want to call it, where this row of a location I comma j is equal to the max of this magnitude found over all the activations at the location I comma j, I comma j comma r. and this is max over all r's. So r for me was varying from 1, 2, 3, 4, 5, 6. So there were 6 possible values of r. So essentially your rho is something which gives you a max value of that. Then what we do is that this theta at a location I comma j is equal to essentially 360 divided by capital R, which is the total number of such things which are to be present, over argmax over this yijr. So now let's look into what that essentially means. What would this indicate? Okay, so what it indicates is something like this, that at a given location, I comma j over here. So at location across the rotated channels are, we find the one with highest activation. So what you are able to do over here is that for any given location, you have different rotated versions of the activation present with you, and that you got by virtue of essentially having rotated versions of the kernel present to you. Now, when you get this rotated version of the kernel and these rotated version of the activations present over there, then you just need to find out that which of these activations is of the highest value. So once you find out which of these activations is of the highest value, then you can just substitute that back over here and say that that is the magnitude of my vector. Okay, it's just a representation over here in terms of a vector field, which will consist of magnitude and it will consist of the direction. So whatever is the highest magnitude at that location across all the rotations which are possible is going to give you this magnitude, and whatever is the angle over there. So if I find out the argmax over r, that is going to give me like, and which particular angle, or so angle is this direction over here. So this is for one, this is 0 degree rotation, this is that 60 degree, this is 120 degree, and like this it keeps on going, and this is 300 degree of a rotation. So at whichever rotated version, I have the highest magnitude coming in over here. For that, whatever is the corresponding angle is what stays. So now if you look into it carefully, what will come in is that this vector field will now get populated by these kind of tiny looking vectors. So dependent on the magnitude is going to be the like length of this vector, and the direction is what is going to be the angle which comes out over here. Okay, so like this it keeps on going, and you will be able to populate and get this vector field. Okay. Now that you have this kind of a vector field coming for one of the kernels, you can actually do this over multiple kernels. So for each of these kernels, you will have to do it separately. Now, if I expand this and write it, then it looks something like this, that I have this x1. I had my first convolution kernel, which I can call as P1. Okay. Now there are a couple of rotated versions of that one. So one of them is what is called as P1 theta 1. There is another rotated version of this one which will be called as P1 theta 2. There will be another rotated version of this one which will be called as P1 theta 3. So as of now we are just going to consider only 4 possible rotations over here. Now you will get down this convolution, you will have this convolution, and then you will have this addition of the bias. Okay. As a result of which, what you get down is a 3D tensor, which will have 4 such of them. So this is capital R is equal to 4, and this is what we will call as Y. Okay. Now from Y, you will do something which is called as orientation pooling, and as a result of orientation pooling, you get down this one which is called as Z1. Okay, so Z1 will have these kind of vectors over there. So this is my vector field. Now, if I have another convolution kernel, which is my P2, then a rotated version of P2 will be P2 theta 1 will be P2 theta 2. Another rotated version will be P2 theta 3. Then you add a bias, and then you get this Y over here, which is Y2, which corresponds to my second convolution kernel, which is P2. You run an orientation pooling, and then you get another vector field, which is say called as Z2. So like this, it keeps on going over here. So now, if I carefully look at it and compare this with my traditional CNN, then what comes out is that as a result of my vector convolution, I will be getting down vector fields instead of a tensor, which is just made out of scalar values. So over here, my tensor, I still get a 2D tensor, but my tensor is made out of vector values, not out of scalar values. Okay, so now comes down my next part, which is sort of like an equivalent of the pooling operation itself. Okay, so that is something. Yes, tell me.
Sir, do we always rotate the means each kernel by 360 degrees, or is it our wish?
What is maximum rotation? If you rotate by 360 degree, you will come back to itself.
Means I'm asking like theta 1 is 60, theta 2 is 120, and can I restrict theta 3 to 150? Or
okay, so we would prefer to rotate it by uniform step sizes of angles. That is what is preferred. You can do it non-uniform as well. What typically we do is we select what is the number of steps in which I want to rotate. So if my capital R is 6, then you will rotate by 60 degree. If my capital R, which is the number of steps of rotation, that is equal to 4, then I will rotate it by 90 degree.
yes, sir. My question was, will like theta R be always 360 degrees, or can it be less than that as well?
Why will it be? So you need to understand maximum angles is how many, what is the maximum rotation which you can do over there, after which you will come back to itself, is 360.
Yes.
Okay, so if you want to stop at some point below that, then essentially you are not covering the complete space.
Yes.
So what we do essentially is that we want to look at maximal coverage over all rotations within that 360 degree thing which we can do. So we choose a step size in such a way that say I rotate by 1 degree or I rotate by 2 degree, more or less they will have the same impact. Okay, but if I rotate by 30 degree versus I rotate by 60 degree, there is a significant change which comes in. So depending on the structural diversity of the particular object in the image which I am taking, this is a designer's prerogative to choose in how many step sizes I would like to rotate my kernels in order to see the output.
Okay.
Sir, can you again explain vector fields?
Okay, so I do something which is called as an orientation pooling or OP. Now, what this orientation pooling does is something like this. So I have a tensor Y1, which consists of multiple such activations, each at a different angle. Okay. So this particular value over here is what is called as YIJR. Okay. R is this index along this one, I is along this, J is along this. So this point is going to be a location which is YIJR. Now what I am trying to do is at any given location I comma j, I try to see across all of these rotations where do I get the maximum amplitude, and why will that come? That comes from the basis of resonance theory itself. So if the kernel matches in its say shape, size and whatever is the value with that of the signal which it is convolving, then it will have the maximum activation. That is what is supposed to be over there. So what I see essentially over here is that if a rotated version of that kernel has an exact match or almost an exact match with the object which is present in the image, then only at that rotated field it will have its maximum amplitude. Okay, now that it will have its maximum amplitude over there, I want to find out what is that maximum amplitude which I get. So I find out maximum amplitude. Next, I also want to find out what is the angle at which I get that maximum amplitude, which is my theta, Ij. So I find out both of them. So combining my maximum amplitude and the angle at which I obtain this maximum amplitude, I create my vector field, which is given like this. Do you get it now?
Yes, sir. Yes. Thank you.
Okay. So now what I will have is I can have multiple kernels. So say in a convolutional neural network, I have two kernels. For each kernel, I can repeat these rotations. So I will essentially get one vector field for one kernel. I will get another vector field for another kernel over here. So I have one kernel, one vector field, another kernel, another vector field. This is what I get. Are we clear till here?
Yes, sir.
Okay. So now the next operation is which is very similar to the max pooling operation in case of a CNN. This operation is what is called as spatial pooling. So spatial pooling is something which is defined like this, that say the vector field after pooling is ZP and I'm looking at a certain location C, then that is equal to Z of a location J. Wait. Because it's in 2D, let me write it appropriately in 2D. You'll get confused between so many tensor notations. ZP at a location M, N is equal to Z at a location I, J, where I, J is equal to arg max over this pooling window, whatever is that W, over all of these row I, J. Okay, so what I'm doing essentially is that I have a vector field. Okay, and let me take this small point over here. So there can be a vector like this and a few vectors like this. So what is my maximum value? My maximum value is over here. This has the maximum amplitude. So essentially, this thing is what is this whole location. This is my maximum value, which goes over here. So this vector gets substituted over here. So in case of a simple max pooling, you were just substituting that value, which was of the maximum. So whatever was the maximum value within that window where you were doing the pooling. here in case of spatial pooling, what we do is that we substitute not just the value, but also the direction of that vector, which has the maximum amplitude. So is that clear to you guys?
Yes, sir.
Okay. So this is about one part of it where you took a scalar field and then you convert it to a vector field. Now, eventually you have the next part of it, which is from a vector field, you can again do vector convolutions and do it, but I will not drag it together today because we are already beyond the class hour. So that is something which I will again continue from in the next class. So anyways, next week we have the test as is scheduled. And after that, when I get back to the class, I will start from this point of vector convolutions.
So syllabus is till this point, sir.
Till this point.
Okay, sir. Thank you.
So can you explore this last? You said that you were taking the the direction. So isn't that location?
Tell me.
So isn't the location of the maximum vector 1 1? So why are we how are we taking the direction here itself? Like ij is the position, right?
Okay, ij is the position. Now Hitesh, look into it. When I do a spatial pooling on a vector field, the output should also be a vector field.
Yes.
Okay. So I picked up my magnitude. I picked up a vector with the highest magnitude. So if I replace that vector to the output, then what is it going to have? It will have the maximum magnitude and the direction will be the same as direction of the vector with the maximum magnitude.
Yes, sir.
That's what I am doing over here.
So this direction will be like the last one which we have calculated theta I comma j.
Yes.
And this ij will be some different location in the
so this is after that. So spatial pooling is essentially analogous to the max pooling operation in a. So this is analogous to max pooling operation in a traditional 2D CNN.
So orientation pooling is it is like max pooling along along the z-axis with 1 by 1 window, 1 by 1 and R window, and
Yes.
this one is
orientation pooling is over there. So orientation pooling doesn't have a 1 by 1 window. Orientation pooling is pulling along the orientation direction, and spatial pooling is pulling along the spatial direction.
Okay, sir. Got it.
Hello, sir.
Yes.
Just could you repeat, sir, once again, what is the importance of the rotation to find the activation value? Because we can find direct way to activation value. No? So why you?
So this relies on the resonance theory of signals. So it's something like this, that say I have a sine wave and my convolution kernel is also shaped like a sine wave of the same frequency. Okay. So when both of these waves match in the phase, then they will have the highest convolution. Will it be so? Do you agree to this?
So, sir, our goal is the maximum amplitude among the all same frequency, right?
Yes. So over here we don't have a frequency. In case of our CNNs, we have certain objects which have a certain nature of representation, and that nature of representation is captured within the convolution kernel itself.
So, sir, in the output, what is the majority change among the rotation, sir?
So if the object is rotated, So now this is where I will go back to my previous slide. So look over here that. So if this apple was rotated and fed to the same CNN, then I was seeing a decrease in my activation. Similarly, if the digit was rotated and fed to the same CNN, I did see a decrease in my activation. The reason for this is that the convolution kernels, which are receptive to that apple's structure or the digit structure, they are receptive to seeing it only in the upright form, not in the rotated version. And because they were not receptive to seeing it in the rotated version, that's why your activation values actually reduced.
Okay, sir. It's mere dimension reduce, right?
No, the dimension is not reduced. The magnitude of the activation is reduced.
Okay.
So Dipankar, I would suggest you that you actually solve a numerical problem around this one. So you take two convolution kernels and so you take a image, you take a some matrix, say a 5 cross 5, and you take a 3 cross 3 convolution kernel. Then you rotate, and in the first case, your values of that 5 cross 5 kernel should be somewhat similar to the value of the 3 cross 3 5 cross 5 image should be the same as similar to the values on the 3 cross 3 convolution kernel. Now what you do is you rotate your original input and then see what is your activation coming from there. And next you rotate your convolution kernel by the same amount and then see your activation. Then you will be able to realize this one.
Okay, sir. Thank you.
So one more question.
Hmm.
So like here, because we are getting the output as a vector field, so
Yes.
there must be one more step which would turn into like where we would get the classification results like 1 and 0 for
I have not yet finished. I have not yet finished. So you got a vector field from a scalar field, from a scalar tensor. So next is from a vector field as an input, you will get another vector field as an output.
Yes,
now from there you will get a scalar field as an output from a vector field as an input. So those two parts are still left.
Okay.
That will take me another hour to finish it. Okay, so let us close for the day, and then we again catch up next week for the exam, and then after that with the class.
Thank you, sir.
Thank you, sir.
Okay, bye.
Thank you.
Thank you, sir.